And the next contribution will be from Beck, who will give us an overview of UK's Department of Chemical and Materials Engineering.
And let's see if I can break as many possible presentation rules at once. And the first one I'm going to try to break is we'll see if I can get some movies to work. But if not...
Don't break the computer.
Yeah. So thanks CAR and the Tri-State Catalysis Club for organizing this. I'm really excited to be here. I'm a new professor at the University of Kentucky. I sit in the Chemical and Materials Engineering Department, and don't be fooled, I really am a materials scientist. And what I'd like to do today, there's been a lot of talk about catalysis and about computation, and I want to try to show some ways that computation can be used to maybe approach problems in catalysis, for example, in maybe non-traditional ways. And to do that, I want to reach back to an area that Dr. Spivey touched on in this application of ab initio techniques, quantum mechanical calculations, to problems in catalysis. But I want to talk specifically about the application of dynamics. And I want to show two examples, neither from the world of catalysis, about how advanced methods based on quantum mechanics, looking at dynamics of systems, might be then translated for application in catalytic systems. And the goal, of course, then is this. This is out of CAR, some pictures of beautiful 5-nanometer Syria cubes. And of course, we're looking at, right now, we're already doing some nice 2-nanometer cubes. We'd like to go to 1,000 atom cubes and get up to about 3 nanometers as well. And you can see how real we can get directly. So anyways, let me step away from catalysis for just a second to introduce a cool dynamical technique. And I want to talk about oxygen conductivity in solid oxide fuel cells. Yttria stabilized zirconia, YSZ, is a classic electrolytic solid for oxygen diffusivity. And recently, collaborators I work with at Oak Ridge reported experimentally the observation of, and no, this is not a misprint, an 8 order of magnitude increase in oxygen conductivity in multi-layered strontium titanate yttria stabilized zirconia layers. Now, experimentally, as soon as you put multi-layers together and you see crazy effects like 8 order of magnitude changes in behaviors, you're immediately going to look at the potential effects of interfaces. And in terms of oxygen diffusivity in a solid, clearly in an interface, you're looking at an increased level of disorder, so it makes sense that you'd observe some enhanced diffusivity there. But the question remains, 8 orders of magnitude, is that what we should expect from a simple interface effect? So the question then came to a computational one, can we actually model such an effect? Is this an artifact of the experiment? Can we get at some reason atomistically why this happened? The answer, of course, is yes, or I wouldn't be telling this story. But let me briefly say how we got that answer, and then we can say a few words about why I think that's useful in catalytic applications. The first thing is the principal effect in the multi-layers is that the yttria stabilized zirconia, schematically shown here, is highly strained or stressed in the multi-layer system. And one of the things we wanted to do was look directly at mobility, oxygen mobility at temperature. So we turned on temperature just by giving each atom a little bit of kinetic energy and did a kind of molecular dynamics simulation, all based on first principles. So purely quantum mechanically calculated forces in a standard commercial code called VASP. And we just let things go. And this is a misprint. This should be about 1,000 Kelvin here. I apologize for that. And basically what happened is, as you let the dynamical system evolve, it rearranged itself into a completely new structural phase. Okay? And you can see that it's not entirely clear here because the heavy atoms, the zirconiums, have stayed pretty much in their same position, while the oxygen atoms have rearranged themselves into this strange zigzag pattern. What this actually amounts to is that you have layers of 4-fold coordinated and 3-fold coordinated oxygens. Where does that come from? You can go into the literature and there's a series of papers on amorphous zirconia, and they report the appearance of 7-fold coordinated zirconium atoms in amorphous zirconia. So that's where this 3- and 4-fold coordinated oxygen comes from. This was pretty cool, but it doesn't directly answer the question about diffusivity. That, of course, comes about when you heat things up. This is 2,000 Kelvin. can see the disorder increasing. And in fact, you then measure the mean square displacement of computation time of individual oxygen atoms. The thing to note here is that in the on-strain case, the cubic fluoride zirconia, without the application of strain, for about the entire length of simulation time, even at 2500 Kelvin, you see almost no motion of oxygen atoms. Okay. In the strain structure that's giving rise to this new phase with 3- and 4-fold gradient oxygens, clearly at 2500 K and even much lower temperatures, you're getting much higher oxygen diffusivity. You can use that to extract, of course, from an Arrhenius plot the activation energy, and it matches very well with the experimental values. Okay, now the point here is that we've used a dynamical technique, okay, molecular dynamics based on quantum mechanics, both to find out new information about bulk structures, but ultimately about a purely dynamical process, that is, diffusion in a solid oxide field cell electrolyte. What does that have to do with catalysis? Let's go back to Syria that Alan mentioned. We know that oxygen vacancies play a key role in controlling catalytic activity. And I've just pulled two of the most recent kind of statements of this from the literature. This is just some EPR results showing two different processes to produce Syria catalysts, one of which shows this huge signal at 1.961 Gauss. And this signal is associated with the presence of oxygen vacancies. And when you translate that over into catalytic activity, directly into catalytic activity here in a carbon monoxide application, you see that it's this structure that has much higher conversion rates and higher activity. The point is, oxygen vacancies are somehow connected to catalytic activity. And there's been a lot of computational work on that, but nearly all of it has focused on, as a question to Alan hinted, at specific arrangements of oxygen vacancies. And more importantly, from the ab initio framework, oxygen vacancies are at or near the surface. The point is, we don't know where the oxygen vacancies want to be, and just guessing at that is an incredibly expensive technique. But, for example, by turning on temperature in a quantum mechanical calculation to letting oxygen move around inside of an actual nanoparticle, you could actually take advantage of some dynamical analysis to look at where oxygen vacancies want to sit, just as a way to get more information about the real systems, the real catalysts that have these oxygen vacancies distributed. So with that, let's throw this whole thing away and break another rule of presentations and try to do two things at once and show you a completely different perspective on dynamical capabilities. What can we do with dynamics? And here I'll steal a picture from before. And what I want to suggest here is that this is a huge amount of computation. It's a great piece of work. It's an incredibly powerful design tool. It maps out for us where we might want to go in manufacturing new bimetallic catalysts. But it's dependent on a kind of traditional picture of catalytic reactions as translated into particularly quantum mechanical calculations, and that is static energy values. Okay, we'll calculate the energy of the products and the reactants and try to get at some transition states using kind of static approximations of what's going on. Wouldn't it be nice if we actually do this reaction? Okay, first question is, why can't we? Well, the point is we can do molecular dynamics and make the atoms move around. But what we generally lack, particularly on the ab initio side, is the electron dynamics piece. Okay? And we haven't lacked it necessarily in a theoretical sense, because for about 20 years has existed a mathematical reformulation of density functional theory. If we can find that's good. There we go. An extension of traditional density functional theory that places DFT in a fully time-dependent regime. So therefore, time-dependent density functional theory solves not just the static ground state cone-sham Hamiltonian, but actually evolves in fully time-dependent sense the Schrodinger equation in a cone-sham-like system. And what's being shown here is what happens if you take a simple gold nanowire. It's only about 6 atoms long, between two little gold electrodes that are just little plates of additional gold atoms as a charge reservoir. That didn't work, so we'll try it again. And initially, a step field bias has been applied to this. That's pooled the electrons to one side, valence electrons to one side of the structure. And then at time 0, which is the beginning of the movie, the field is removed, and what you're watching is the change in charge density as electrons slosh back and forth through the system. The point is, using TDFT-based methods, we can actually calculate the transfer of charge in fully dynamical real-time, obviously not computationally real-time, but a real-time practical way to get at what are electrons doing in dynamical systems. Maybe more of interest to catalytic reactions, we can actually do this with individual atoms that have ion motion. The nuclei are moving as well as the electrons. You can make them bump into each other and watch as the excited state develops. You're looking at charge density plotted in color again, and what you might be able to see here is this beautiful oscillation that's left behind, this atom here. And that's simply the characteristic of the time-dependent excited state. The suggestion that I want to make to you is that in terms of catalytic reactions, we have these great kind of tools that allow us to search possibilities. And I think we can add, based on some really advanced techniques like TDDFT, pieces of dynamical information that bring us that one more step closer to the real system. We're no longer limited to static non-state properties. With that, I'd like to take any questions you have. Thanks.
Can you deal with changes, let's say, in the morphology of a cluster on a surface in a time-dependent way as reactants are, bonds are broken, bonds are formed, and
yeah, and let me switch back over. The actual